Hello everyone, and welcome to today's webinar. My name is Sahar Paksad. I'm the Marketing and Communications Coordinator at Klohn, Crippen, Berger. In today's webinar, we will talk about the diversion tunnel orifices for energy dissipation during reservoir filling at the Site C Clean Energy Project. If you have any questions during the webinar, you can submit them in the questions box in your GoToWebinar toolbar. We will compile the questions and we'll send you a summary of the questions and answers after the webinar. Also, a copy of today's presentation is available to download from the handouts box in the webinar toolbar, which is just under the questions box. Lastly, an on-demand recording of this webinar will be available on our website at klohn.com. You will get an email about it as well. So today's presenter is Jeremy Bruce. Jeremy is one of our civil engineers here at KCB. His focus is on hydrotechnical engineering. He has 12 years of broad experience in the management and design of hydroelectric and water resource infrastructure projects. Jeremy has worked on a range of hydroelectric projects, from small redevelopments to large new constructions. He specializes in the hydrotechnical design of spillways, tunnels, powerhouses, and water conveyance systems, including power intakes and penstocks. In this presentation, Jeremy will provide a brief overview of the Site C project and will present a summary of the alternative evaluation for reservoir filling that took place during the design. He will then focus on the selected reservoir filling alternative, which is a unique solution in North America. Over to you, Jeremy.
Thanks, Sahar. And I'd like to welcome everyone to the third webinar in this series presented by Klohn, Crippen, Berger. Thank you very much for taking the time to attend. So as Sahar said, this presentation will focus on one very interesting aspect of the Site C Clean Energy Project design that I was fortunate enough to be involved with. This aspect relates to the reservoir filling and passage of downstream flows through the diversion tunnels. So let's begin. Before I start, I'd like to acknowledge my colleagues on the Site C engineering team from BC Hydro, Klohn, Crippen, Berger, and SNC-Lavalin, many of whom participated in the design of this topic I'm going to present today. I'd also like to acknowledge the following co-authors of a related paper that was presented on this topic at the 2017 Canadian Dam Association Conference. John Krokowitz, a former BC Hydro employee, Faisal Yusuf, who's a current hydrotechnical engineer at BC Hydro, John Nunn, formerly with Klohn, Crippen, Berger, and Andrew Watson with BC Hydro. So I'm going to start off with a brief introduction to the Site C project. It's a fairly high-profile project, so I'm sure many of the listeners have at least heard about it or are somewhat familiar. Site C is a hydroelectric facility currently under construction on the Peace River in northeastern British Columbia. I won't talk too much about the current status, but I will say that Site C is coming up on 3 years of construction, with another 5 years remaining until the scheduled first power generation, which will be approximately late 2023. So the Peace River flows from west to east, starting in northeastern British Columbia in the Williston Reservoir. The Peace River flows past Fort St. John into Alberta and then north towards Lake Athabasca and into Great Slave Lake in the Northwest Territories. You can see here the location of the proposed Site C dam right near the city of Fort St. John. Site C, when completed, will be the third dam on the Peace River, downstream from the two existing facilities, which are the WAC Bennett and the Peace Canyon Dam. Site C will be approximately 83 kilometers downstream of the Peace Canyon Dam on the Peace River. Because of this, Site C is able to take advantage of the storage in the Williston Reservoir to generate a fairly large amount of electricity with a relatively small reservoir footprint. You can see from this map here, the large Williston Reservoir, which is impounded by the WAC Bennett Dam, the smaller Dinosaur Reservoir, impounded by the Peace Canyon Dam, and the proposed Site C Reservoir with the dam near the town of Fort St. John. So the Site C project was first contemplated in the 1980s, and the dam axis identified at that time is actually very close to the present location. Now here's a little piece of trivia. The name Site C, where does that come from, you might say? Well, the answer is actually quite straightforward. During some of the early investigations into the Site C project, there were a number of different dam axes identified as possibilities. Those ranged from Site A, which was the most upstream dam closest to Peace Canyon, all the way to Site F, which was the most downstream location. Site C, which was one of the ones in the middle, was identified as the preferred location for a number of different reasons, and that brings us to the name Site C that we still use today. Here's a few key facts about the Site C facility, and this is an architectural rendering you can see on your screen. So Site C will be an earth-fill dam. The dam length at the crest is just over 1 kilometer. And the height of the dam is about 60 meters from the riverbed up to the dam crest. The capacity of the Site C generating station will be about 1,100 megawatts with an energy production of about 5,100 gigawatt hours per year. The reservoir length upstream is about 83 kilometers to the toe of the Peace Canyon Dam upstream. And the width of the river will be about 2 to 3 times the current river on average. Some of the other components you can see here on the screen are the spillway, which is composed also of an auxiliary spillway, the transmission lines, which go over the approach channel to the left of the screen, and the Site C substation. Here we have another rendering showing some of the key components of the dam site. The presentation today will focus on the north bank of the river, which is on the right side of your screen, where the Site C diversion tunnels are located. You can see here the diversion tunnel inlet and outlet labeled on the screen. The tunnels are in the bank of in the left bank on the right side of your screen. They form a U shape around the earth-fill dam. You can also see the reservoir and a representation of a debris boom upstream of the dam. Then you can see here the approach channel on the left side of your screen. That conveys water from the reservoir to the power intakes and the spillway. Also have an outline shown of the RCC foundation, which RCC stands for roller compacted concrete, and that's a foundation that will be built underneath the key dam structures, including the spillway and the power intakes and powerhouse. Here's a schematic view of the diversion tunnels on the north bank of this at the Site C dam site. You can see the inlet structures at the top of your screen. The tunnels go into the bank around the earth-fill dam and out the bottom of the screen at the outlet structures. Each of these 2 tunnels will be approximately 10.8 meters internal diameter, and each of the tunnels will be concrete lined. The length of each tunnel is about 800 meters, and these tunnels will be designed to pass the entire Peace River flow for approximately 3 years during construction of the earth-fill dam. The tunnels are designed to pass a fairly significant flood event during construction of the dam, and I'll talk a little bit more about that on the next slide. So the Site C diversion tunnels are designed for a total flow of up to 3,000 cubic meters per second. And the Site C environmental impact statement establishes a minimum downstream flow during construction and during permanent operations of the Site C facility of 390 cubic meters per second. So during reservoir filling, the water levels are quite low, and water has not yet reached the level to pass into the approach channel and feed into the power intakes or the spillway. So at the start of reservoir filling, we needed a way to pass the minimum 390 cubic meters per second downstream while allowing the reservoir to fill at the same time. So this was really the core design challenge, because the diversion tunnels are designed to pass a large amount of flow during construction. But in order to fill the reservoir while maintaining downstream flows, we needed to restrict the flow capacity through the tunnels. Now, the obvious solution was to shut one of the two tunnels and perform reservoir filling with only one of the two tunnels operating. But unfortunately, due to the large size of that tunnel, 10.8 meters internal diameter, the capacity is still too great to allow reservoir filling with normal flows from upstream. So we had to investigate some alternative arrangements to be able to pass those flows while filling the reservoir. Now, this first stage of reservoir filling is done with the diversion tunnels passing flow downstream. But once we get up to the approach channel level, which is about half of the reservoir filling, then we are able to pass downstream flow through the spillway. So then the diversion tunnels are closed and are no longer used for passing flow downstream. But it was really this first stage of reservoir filling that is the topic of the presentation today. So before we started looking at different arrangements, we wanted to establish some key criteria for evaluating our design alternatives. So we came up with a list of some key criteria that we wanted to use to evaluate our alternatives against. The first criteria is a translating hydraulic jump. So what I mean by this is we did not want to accept a final arrangement that would involve a hydraulic jump moving up or down the tunnel in different locations depending on the reservoir level. That would expose the tunnel to risk due to pressure fluctuations and the moving hydraulic jump, and it would also expose the outlet structure to potential risks from those pressure fluctuations. So we didn't want an arrangement with a moving hydraulic jump. The second criteria was vibration of the upstream control gate. So each tunnel has an inlet gate, which is designed to open and close. That inlet gate must open and close without issue at final closure and during initial diversion. So we didn't want to accept an arrangement where vibration of the control gate could potentially damage it or cause increased risk. So that was our second criteria. The third criteria was the impact on diversion. So as I said before, the tunnels will operate for 3 years to pass the Peace River flows during diversion. We did not want to impose any additional losses or impacts on that diversion period or in the diversion tunnels, so that we increased risk of overtopping of the cofferdams during construction. So we wanted an arrangement that would not impact the diversion tunnels during that 3-year construction period. Our fourth criteria was constraints on upstream generation. So because there are 2 generating facilities upstream of Site C, there is some ability to control inflows to Site C during reservoir filling. But we did not want to impose excessive constraints on those facilities because they provide a large proportion of the province's energy in British Columbia. So we wanted an arrangement that could fill the reservoir without putting extreme constraints on the upstream facilities. Our fifth criteria was geotechnical risk. So we did not want to accept an arrangement that would impose excessive geotechnical risk due to either pressurizing the north bank of the dam, pressurizing the rock from increased water levels in the tunnel, or any other pressure fluctuations or perceived increase to the geotechnical risk. The sixth criteria was sensitivity to uncertain parameters. So we wanted a robust arrangement for reservoir filling that was not overly sensitive to some of the uncertain parameters, such as the tailwater levels downstream of the facility and some things that we would not know with great certainty until the arrangement was actually operating. Our seventh and final criteria was total dissolved gas. Now, total dissolved gas, or TDG, is an important criteria for a number of the features at Site C, including the spillway. So we wanted a reservoir filling and diversion arrangement that would not increase the total dissolved gas and potentially harm fish downstream. So that was our final key criteria. So we evaluated a number of different alternatives for reservoir filling, looking at the key criteria on the previous slide. I've put a list here of a few to give you an idea of some of the things that were looked at. So the first alternative that was reviewed was inlet control by gate regulation. So this was one of the options that was raised during historic design of Site C in the 1980s. They were looking at partial closure of the upstream regulating gates, which effectively reduces the flow through the tunnel. But the reason we didn't like this arrangement was because it generated the translating hydraulic jump, or a moving hydraulic jump, which, as you recall in the previous slide, was something we did not like due to the risk to the tunnel and the tunnel liner. The second alternative we looked at was modifying the diversion tunnel diameters. So as I said, both tunnels have an equal diameter of 10.8 meters. So we did consider building one larger tunnel and one smaller tunnel, which would allow us to only use the smaller tunnel during reservoir filling. However, due to constraints in the rock for the larger tunnel diameter, we did not want to go much larger than the 10.8 meters that we already had established. So that did not allow us to consider largely different tunnel diameters for the two tunnels. So we didn't like that option either. The third option we looked at was building an entirely third diversion tunnel just for reservoir filling. That would be a much smaller tunnel than the 10.8 meters, and it would achieve the required criteria. But as you can imagine, that would be a very expensive solution and not something that we wanted to accept until we exhausted our other alternatives. Option 4 was modified inlet structure. And so there was a number of sub-options that were considered under this, but basically we were looking at additional inlet ports or openings in the inlet structure to allow for flow without regulating using the upstream gate. Now, some of these options did look favorable, although the primary concern was vibration of the main upstream control gate in the diversion tunnels. The fifth option we looked at was a right bank low-level outlet through the RCC buttress. So this would eliminate the dependency on the diversion tunnels during filling and would have filled the reservoir using a low-level outlet. However, the RCC buttress is a permanent structure providing stability to the key dam components. And we ended up ruling out this option because of the potential for increased risk of stability of the right bank. The sixth option was an outlet control alternative. So this would have involved putting some kind of control gate or control structure at the downstream end of the tunnel. This was favorable hydraulically. However, the increased risk due to increased pressurization of the tunnel, increased geotechnical risk, was not something we wanted to consider further. The seventh option, which I'm going to show a little bit more in the next slide, was a forced hydraulic jump. So we didn't like the first option, inlet control by gate regulation, because of the hydraulic jump moving up and down the tunnel. But we thought maybe we would be willing to accept this arrangement if we could keep the hydraulic jump in a known location near the upstream end of the tunnel. So I'll show on the next slide, we did some further analysis on this option. Here's a couple of plots showing some of the additional analysis we did on a forced hydraulic jump option. In this case, we called it a baffle sill. So the left picture is a plot from the software Flow3D. It's a CFD, or computational fluid dynamics software. And what this is showing is a partially closed gate at the upstream end of the tunnel, with flow passing at a high velocity underneath the gate. And then the flow impacts this low concrete sill in the tunnel, which forces the hydraulic jump to occur at this location and not move further down the tunnel. The CFD analysis showed favorable results and something we wanted to investigate further. So on the right side of the screen, you can see a picture of a physical hydraulic model that was constructed, and we tested the baffle sill in this model. Now, in the physical model, the baffle sill did not show very favorable results. There was quite a lot of air entrainment and excessive pressure fluctuations. And so at this stage, the baffle sill arrangement was also eliminated. So this brings us to the selected reservoir filling design, which is described as a series of inline orifices, which will be installed in tunnel number 2. That's the outer and slightly longer of the 2 tunnels. The orifices will be installed in tunnel 2 after the 3-year diversion period, but just prior to reservoir filling. Now, these orifices are effective at adding local losses into the tunnel and reducing the flow capacity of the tunnel significantly. The design of these orifices was modeled after a successful precedent project in China, the Xiaolangdi hydroelectric project. Now in Xiaolangdi, they actually use these orifices in a permanent spillway tunnel. There's several of the spillway tunnels actually for long-term operation. So that's the biggest difference with Site C, is that we will be using these orifices for a fairly short-term period during reservoir filling, and then the diversion tunnel is plugged and decommissioned and not used again. But these orifices were effective and have operated since 2010 in the Xiaolangdi project for permanent operations. So the flows through the diversion tunnel using these orifices start at about the minimum downstream flow of 390 cubic meter per second. That's at the start of reservoir filling, with a water level, an upstream water level of 425 meters. And that flow only increases to about 535 meters cubed per second at the maximum filling level of 440 meters. And that's where we transition over from the diversion tunnels to the spillway for downstream flows. So that's at elevation 440, the diversion tunnel will be closed. Now that flow increasing from 390 to 535 is done without any upstream regulation of the gate. That's with a fully open tunnel, just with the orifices restricting the flow capacity. So here's a couple of more detailed views so you can see what these orifices look like. The picture on the left shows a section view looking straight at one of the orifices. So the smallest circle in the middle would represent the opening that flow would have to pass through the orifice. And the other lines represent cross-sectional features of the steel looking at the orifice. The opening in the orifice is approximately 70%, the diameter of the opening, I should say, is about 70% of the internal tunnel diameter of 10.8 meters. And the right view shows a detailed cross-section looking through the orifice. Flow would be traveling from the left side of this view to the right side. So there's an upstream wedge, which is part of the orifice design. That was modeled after the Xiaolangdi project, which found that this wedge was quite effective at improving the cavitation performance downstream of the orifice. The steel plate has a small radius on the upstream lip here. You can see it's shown as 60 millimeters, and a downstream slope. For the Site C arrangement, the steel plate will form the orifices and will be installed with embedded plates and welded to the embedded plates in the concrete liner. And the orifice will also be infilled, the steel will be infilled with concrete. Now here's a view, a plan view looking down on the 2 diversion tunnels in the north bank of the Site C dam site. This view shows where the 4 orifices will be located in the diversion tunnel. So the diversion inlet is on the left side of your picture. And the first orifice, orifice number 1, is located just shortly downstream of the inlet structure. Then we have a gradual bend in the tunnel and a series of 3 orifices, number 2, 3, and 4, are located in the straight segment of the tunnel just downstream of the first bend. Now there was a couple of criteria we used for locating these orifices. We did not want to locate an orifice within the tunnel bend. That would create unsymmetric flow conditions that would be undesirable. We also wanted all 4 orifices to be located upstream of the future Site C dam axis, which is represented by this center line here. The reason for that was that we did not want to impose additional pressure into the left bank beyond the dam axis, as that would not be pressurized after completion of the earth fill dam. So we wanted all of those increased pressures to occur upstream of the future dam axis. You can see here that orifice number 4 is actually located at the downstream end of the future tunnel plug, which is shown in gray. That was an additional feature that will help with forming of the tunnel plug during tunnel decommissioning. Now, here's an additional view showing a profile through tunnel number 2 with the 4 orifices. So 2 of the key criteria we used during design were the hydraulic losses, or the hydraulic gradient in the tunnel, and also the cavitation performance. So the final diameters that were selected, each of the orifices actually has a slightly different opening diameter in the center. The first orifice has the smallest opening at 0.68 times the diameter of the tunnel, and the openings get slightly larger as you move downstream. Now, this might seem a little bit counterintuitive, but the reason for that is that each of the orifices has a reduced downstream pressure or a reduced back pressure as you move downstream. So we actually wanted the most loss at the first orifice, where we have the highest downstream pressure. That was important for the cavitation performance. You can see from this profile that the tunnel slope was actually modified due to the addition of the orifices as well. Tunnel number 1, which doesn't have any orifices installed, is a constant slope from the inlet structure to the outlet structure. But tunnel number 2, we modified it so it had a slightly steeper initial slope, shown here at 5.2%, and then a flatter slope from about orifice number 2 to the end of only about 0.2%. The reason for that modification was to increase the downstream pressure as much as we could on orifice number 2, 3, and 4, which was also done to improve the cavitation performance. Now I'll show a couple of slides with some of the design investigations, or the design techniques that we used to look at these orifices in detail. The first one we used was CFD modeling, or computational fluid dynamics. We used the Flow3D software to provide insights into the velocity patterns, pressure distributions, and the discharge capacities of the tunnel. One of the most interesting things that we found from the CFD modeling and the visualization was the interaction between orifices. So you can see from the image at the bottom left of your picture, this was one of the early designs for the orifice arrangement. The first orifice is shown here, where the velocities begin to increase, and the second orifice just downstream. Now you can see from this color plot that the contracted jet from the first orifice has actually not expanded back up to the full tunnel diameter by the time it reaches the second orifice. Now what that meant is that the second orifice was not nearly as effective at reducing energy as the first orifice, and that was something that we didn't want to see. So because of this visualization, we were able to observe that we wanted to increase the spacing between the orifices, which was put into place for the final design. We also saw excellent agreement between the results of the CFD modeling as well as the physical hydraulic modeling, which I'll show on the next slide. You can see from the picture on the right that we had some very interesting visualizations of the flow through the orifice and some of the maximum velocities. And we were also able to obtain pressures at any point of interest and validate those using the physical hydraulic model. So we also constructed a physical hydraulic model. The model was done at the LaSalle NHC lab in Montreal, and 2 different size models were constructed. The first one was a 1:40 scale, which represents a 10-inch pipe, and that was the primary model used to model the orifices and do all of the pressure investigations for the final orifice arrangement. A slightly larger 1:20 scale model was also constructed. That's about a 20-inch pipe representing the diversion tunnel. And that option was primarily used to test some of the free surface alternatives, such as the baffle sill and the translating hydraulic jump. We needed that larger scale for the free surface problems, whereas the smaller scale, or the 1:40 scale model, was effective at looking at the orifice arrangement, which is a closed conduit pressure flow situation. Here is an output plot from one of the physical hydraulic models, which shows the pressure profile of the final orifice arrangement in tunnel 2. The blue line shown on the screen is at the start of reservoir filling. So you can see this represents a water level of about 425 at the upstream end of the tunnel. Each of the orifices imposes a loss, which drops the pressure profile at each of the orifice locations. And you can see for the red line represents the final elevation for operation of the diversion tunnel with the orifices before the spillway takes over downstream flows. So the red line has higher pressures and larger losses at each of the orifices. And you can see that at orifice number 4, the red line dips just below the crown of the tunnel. So that represents some slightly negative pressures in the tunnel just downstream of orifice number 4. Now, we carefully considered and looked at that in detail in both the physical hydraulic model and the CFD model results, and determined that those negative pressures were in the center of the flow column. They were also just barely negative, not something to be overly concerned about. But we looked at those in detail, and we were satisfied that our design was able to safely accommodate those pressures and would operate effectively. Now, this plot shows a rating curve to compare the diversion tunnel in its 3 different operating conditions. The green line represents the normal diversion tunnel rating curve. So this rating curve would be applicable when both diversion tunnels are operating during that 3-year period during earthfill dam construction. So you can see that the diversion tunnels at an elevation of 420, say, can pass a flow of about 2,000 cubic meters per second. Now, when one of those tunnels is closed, we move from the green line to the blue line, which represents only one tunnel. And I should say the green and the blue line there's no orifices in the tunnel yet, just a wide open tunnel. So moving from the green to the blue line, we close one of the tunnels, and then at the same elevation of 420 meters of upstream water level, we can only pass a flow of about 1,100 cubic meters per second. Now, when the orifices are installed in the diversion tunnels, that capacity restricts even further. So you can see here at an elevation of 420 cubic meters per second, the flow through the diversion tunnel would be about 300 or 350 cubic meters per second. So this slide really just indicates how effective the orifices are at reducing the tunnel capacity. Now, I thought I would finish up by showing a few photos of some of the modeling that was done. So this slide here represents some images from additional diversion gate testing that was done actually subsequent to the physical hydraulic model photos that I showed previously. So this model was done to look in detail at the diversion inlet gate and any vibrations or loads on that gate of interest. It was also done at the LaSalle NHC lab in Quebec, and it was done on the 1:20 scale model, or the 20-inch diameter pipe representing the tunnel. You can see on the picture on the left, which shows the entire model, the wooden structure at the back is a head tank or a head box, which contains the flow and represents the upstream reservoir. The gate would be located right here, and then this curved section is the first bend in the tunnel. Now, the first orifice was modeled during this testing. It was located approximately where my mouse is showing here. The middle picture on the right here is a representation of the gate. Now, this model did quite an accurate representation of the gate. The gate was modeled out of aluminum, and the weight was scaled to the effective prototype weight, was accurately scaled in this model. And the picture on the far right is a representation of the same gate within the guides that it was operating in the model. Finally, I have a few pictures from the Xiaolangdi, which was the dam in China that used these similar orifices. These pictures were taken from a book that was written on the Xiaolangdi project. And I should say that the Xiaolangdi orifices were constructed slightly differently than the ones at Site C. They were constructed in advance before spillway operation. So they are actually largely formed in concrete with just a steel plate on the lip of the orifice. You can see here on the left picture, these workers are constructing the steel lip, but the rest of the orifice would be entirely in concrete. And that's, you can see the heavy reinforcing mat in the background. The pictures in the middle show a little bit more detail of the top view of the opening in the center of the orifice. And the bottom view is something similar to the detailed view I showed earlier with the upstream wedge and the radius on the upstream lip. You can see the scale with one of the workers in the background. The two pictures on the right represent the tunnel on the top right, the tunnel in the finished condition. That's the opening through one of the orifices. And on the bottom right, we see one of the tunnel formwork, which was put in to help with the concrete lining during tunnel construction. And that's my final slide. Thank you very much for your time. I will say that if you have some additional, or if you'd like some more additional information on the Site C project in general, I would suggest going to sitecproject.com. There's some great up-to-date construction photos, schedules, and a whole bunch of other great information on there.